Hi, welcome to the Blackboard. And so, as you can tell by the video, this is going to be another linear proof. As I mentioned in the lecture, that I'll be doing about a proof or two. So this is going to be one of them. And this one will kind of be the real spectrum theorem that I discussed in lecture. However, this is not the general proof, mostly because it is beyond the scope of linear algebra, but I can show you an example for a 2 by 2 matrix. And so we're just going to go ahead and get started. So we're going to have to prove that this symmetric matrix, that is a 2 by 2 matrix, is diagonalizable. And so the first keyword is diagonalizable, so you know what that means. It means that we have to take the characteristic equations and find our eigenvalue. And so we're just going to go ahead and do it. So we have the determinant of a minus lambda, c, and then b minus lambda, and that is equal to 0. We're going to expand that to a minus lambda times b minus lambda minus c squared. And so what I'm going to do now is I'm going to expand this portion here. So we will be getting not a squared, ab plus lambda squared minus a plus b, all in parentheses, times lambda. Bring down the c squared, so it's minus c squared. And so what I'm going to do now is going to combine the alike terms. And what I mean by that is just pretty much put the ab and the c squared together. So we'll end up getting an equation like this. So we have lambda squared minus parentheses a plus b, and then multiply that portion by lambda, plus in parentheses ab minus c squared. And so this is a quadratic polynomial with respect to lambda. And so we'll have our constants L, M, N, where L is equal to 1, M is equal to negative a minus b, I just distributed the negative, and n is equal to ab minus c squared. And so I am not going to solve the eigenvalues here, mostly because it's not gonna tell us anything. But what we can do is take the discriminant of this polynomial, and this will tell us if we're gonna have a real solution or a non-real solution. And so if you remember back in algebra 1, we knew that the discriminant will be equal to m squared minus 4ln, and so that will be equal to negative a minus b quantity squared minus 4 times 1 because of the L, so times 1 times ab minus c squared. So I am going to expand this a little bit and see if I can cancel anything out or simplify it to all in one equation if possible. So we're just going to expand the negative a minus b quantity squared, so that will give us a squared plus b squared plus 2ab, then distribute the 4, so we have minus 4ab plus 4c squared. So again, we're going to combine our like terms. We can combine the 2ab and the negative 4ab, and so we'll be getting a squared minus 2ab plus b squared plus 4c squared. And so what we can do here is we can factor or reduce this portion to a minus b squared, and then bring down the 4ac. So, or not the 4ac, the 4c squared, and that will be our discriminant. And because our discriminant is a sum of two squares, then that is a very good thing, because this tells us that this equation will always be greater than or equal to 0. And so what happens if this is equal to 0? So if this is equal to 0, then we know that we're going to have a minus b quantity squared plus 4c squared is equal to 0. And what this tells us is that c is going to equal to 0 and a is going to equal to b. And we're going to end up getting a matrix that is a, 0, 0, a. and this is already diagonalized. So this already tells us that this is diagonalizable because it's already diagonalized. And on the other hand, if this discriminant is greater than 0, so if greater than 0, then we can use the quadratic formula. That's how you not spell it. Quadratic formula, or any other method if possible, to find our eigenvalues. And this will be pretty much the characteristic polynomial. And we'll know that the eigenvalues will be two distinct roots because the discriminant is positive. So that means all the roots of the characteristic equation will be real. And so this is going to give us two distinct roots, which implies that A has two distinct real eigenvalues. And because there's two distinct eigenvalues, they'll come in with their corresponding eigenvectors. So we'll have two eigenvectors, which is the same number as the number of columns in our matrix, which is 2, therefore telling us that A is diagonalizable in this case. And so that's pretty much it for this video. This was pretty much it for the proof. And like I mentioned, this is not the general proof for the real spectrum theorem. This is only for a 2x2 matrix. So hopefully you learned something about this and solidify the fact that given a symmetrical matrix, that we know that all the eigenvalues are real. The matrix is diagonalizable, and I believe there's another thing. All the eigenvalues are real. No, yeah, all the eigenvalues are real, and the matrix is diagonalizable. So thank you very much, and I'll see you in the next one.